Hello, I'm Bart Stuck. I'm going to be talking today about the evolution of programming languages, starting in the early days with machine language and working up to much more modern languages today that we use, such as Python. So just bear with me, and here's our presentation, and let's start. Um, we begin with the John von Neumann model of computing. It consists of the following pieces: some sort of input device, some sort of output device, could be the same device, a central processing unit that has the control of things, as well as it carries out arithmetic and logic functions. And then there's a storage system, a memory unit. Now they're all interconnected. What's hidden here is by a switch fabric, something that interconnects all these diverse things to make up this model of computing. And we still use this today, and it follows what's going on. So let's start by just looking at some applications that arise from computers. Initially, there was a push on scientific computing, and that's still there today. The scientific computing really focuses on developing algorithms and software for very complex mathematical problems. It's typically very high performance. This leads to the term supercomputers that are used for simulations, for data analysis, for complex computation. So today, for example, much of the work done in climate modeling is done on supercomputers. Then at the other extreme, we have what are called embedded systems. These are systems that are just designed to perform a specific function. That could be, for example, the doorbell camera that has a little computer in it that controls ringing the doorbell and the camera and recording what it sees and so forth, just as one example. So there are all kinds of applications from embedded systems found in both commercial and industrial side of things. And they're really designed to be bulletproof, no human intervention, and they work, respond immediately to any issues. Like if the nuclear reactor core starts to overheat, you will automatically drop in control rods to cool things down faster than a human being could react to this. Then the third category we look at is commercial computing, which is very widely used in business and commerce. It's what we would find, for example, Amazon runs on for its logistics, for moving packages from A to B and storing up who paid what when for all the different things that are bought and sold. The large consumers of this commercial computing include healthcare, which just continues to mushroom, finance, and then the retail side of things. If you go to a grocery store, you'll immediately see all kinds of computers there that make it possible. So in these different segments, what we see is that if we looked at the scientific computing segment, it's already tens of billions of dollars a year. It's forecast to hit 50 billion in 2028. The embedded systems market is even bigger, projected to be 163 billion by 2031. And then the commercial computing market is really the biggest of them all. It's already roughly 150 billion and is expected to grow to 270 billion in just 5 years. So huge markets. Now, in scientific computing, there's really two key people. Seymour Cray, shown here with his very first supercomputer, the Cray 1, and Burton Smith, shown here. Seymour Cray ended up pushing the limits of computers by going faster and faster in a serial manner. So if you made every piece, uh, every segment of what has to happen in a computation speeded up, which he was an expert at, then you would get a faster and faster computer. And he pushed the limits here. If you looked at there's a website called Top 500 computers.com, something like that, .org. And it shows there's a set of benchmarks, software programs that are executed on these computers, and whoever gets done first, that time determines where they're ranked in this list of computers. And for years, Seymour Cray's computers from his Cray research were right up there. What happened over time, though, was you reach a limit here when you can only make things so fast, and then the extra speed that you gain just doesn't pay off as much as doing things in parallel, which is the second way of achieving high performance. And Burton Smith was a master at this. He went through several different companies. In fact, his final company ended up buying Cray computers, and Cray is now one of the leaders in parallel computing. Seymour and Burton are no longer with us, but Burton was able to be a master at achieving concurrency in many, many different ways with multiple processors and so forth. And we see this in the data centers that Google and Facebook and Amazon and Apple have, where there are servers there, and they're running a set of algorithms, and it's possible to run those so they don't compete with one another. So as you add more and more servers, the overall throughput rate goes up. The time that's involved in processing each of these things is the same. That doesn't change, but by having the overall throughput rate go up, that's sufficient to hit whatever performance levels you're looking for. So what computer languages do these different segments use? In scientific computing, the most popular are C and C++, and increasingly Java and Python. And there's a new language that researchers at MIT have developed, a tensor language, which is specifically designed for image processing and deep learning type applications using tensors, which is a generalization of a vector. We have in embedded systems, the two most popular programming languages used there are C and C++. And in commercial computing, the most widely used commercial computer programs is COBOL. That's still the case today, hard as it is to believe, but COBOL has evolved significantly. It's now object-oriented, and it reads very much like regular English. And because of that, that's why it was originally developed and commonly used in business and administrative software applications. So if we now look at the top 5 largest programs ever written, the Human Genome Project, I think, takes the cake. This started in 1990, ended in 2003, and led to 3,300 billion lines of code. The coding took more time to do than the actual sequencing of the human genome, but so be it. And there now is a human epigenome project ongoing, which is adding to this incredible amount of lines of code as well. Something we're all familiar with, Google is probably one of the largest software programs ever written. It's got over 2,000 billion lines of code and growing, especially with the advent of artificial intelligence. We have the average high-end car. You know, this might surprise a lot of people. I mean, cars are cars, what's going on? But there's a lot of software in cars now. And for high-end cars, things like Teslas and so forth, there's really a ton of software in there that leads to tens of millions in hundreds of millions of lines of code, and that's just in one car. And so if you have thousands of cars, so you can or millions of cars, you can see how it scales up. And C++ is the most popular language for doing this for cars. Then we have the operating system for the Macintosh, which is really evolved out of Unix, and it contains over 85 million lines of code. So this is what you would find on your iPhones and Macintosh computers. And then Facebook. Facebook is probably over 60 million lines of code and mushrooming with the advances in artificial intelligence. So here's a little summary in 2023 of the top programming languages. It's a little deceptive because it shows Java here, and that's normalized to be 1. Python. So then Java is here, C++ is here, C is here, JavaScript is here, and so forth. So it goes. HTML, that of course is used on the web, is there. R, which is used for statistical data analysis, in particular in genomics, but also on Wall Street for quants, is very widely used, and so forth. So that's this raises the question here of what language does a computer use? Well, the computer uses machine language. This is a program in binary format, and all of the early computers used assembly language. They were a symbolic representation of machine code, but the assembly code was converted into an executable machine code by a utility program, which is called an assembler, not surprisingly. So this is relatively high time intensity for developing robust software, because it's easy here to make inadvertent errors or to create situations which are very difficult to detect, that are wrong, that you don't want to end up in, let alone recover from. And those are much more easily handled by higher level, more robust software packages than assembly language, but it's out there. A lot of military weapon systems, for example, still have these things. So a higher level programming language is a language that enables the development of a program in a much quicker, more easy to an end user to do, and more abstract, without having to deal with all the details that you encounter in assembly language with the computer's actual hardware or the processor structure here. So here we're dealing with things like Fortran, COBOL, Java, Python, C, C++, and we have a program called a compiler that translates the high-level language statements to machine code here. An example of this computer is the Apollo guidance computer. This is a digital computer that was produced for the Apollo program. One was on the Apollo command module, and another was in the Apollo lunar module, which they were joined together. They went into orbit around the moon. The command module stayed in orbit. The lunar module landed on the moon, then came back up, rejoined with the command module, and went back to Earth. So the Apollo guidance computer provided the computation, the electronic interfaces for guidance, navigation, and control. And this was actually the first computer based on silicon integrated circuits. And it worked. There were 6 successful Apollo missions that landed on the moon, and a 7th that no one died, but it circled the moon and came back, Apollo 13. So the thing that's hard to appreciate here is that this computer that was developed in the early 1960s, and it flew in the late 1960s and early 1970s, is actually comparable to the first generation of home computers from the late 1970s, such as the Apple II, the TRS-80, and the Commodore PET. the Apollo guidance computer had a 16-bit word length, 15 data bits, 1 parity bit, and most of the software is stored in special read-only memory here, fashioned by weaving wires through and around magnetic cores. And there's a small amount of read-write capability in the core memory that's available. So the only way that the astronauts could communicate with this Apollo guidance computer was they had a numeric display and a keyboard called DISC-key for display and keyboard. And the Apollo guidance computer and its DISC-key user interface were all developed in the early 1960s by the MIT Instrumentation Laboratory, and they first flew in 1966. The thing to keep in mind here, the instruction set is today what we would look on as vanilla, but this was the first time anyone had done this that we're aware of. The instruction format had 3 bits for an opcode, 12 bits for an address, and there were a block 1 that had 11 instructions shown here, and then there were the 8 basic instructions were directly accessed by the 3-bit opcode, and the final 3, that is remember there's 8 here, so there's 3, 9, 10, and 11, were denoted as extra code instructions. So there was a special extend that was run here to give a total number of instructions of 33. So 33 instructions here. The total storage in this was 77,000 kilobytes, which today we would look on as absolutely nothing. But that was all that could be afforded for back then. Here's some examples of the Apollo guidance computer instruction set. There's an add, a jump, a load, a complement, an exchange, a no-op function, a count, compare, and skip, and then this index instruction we talked about. So an example of a simple program using this Apollo guidance computer instruction set is to sum the first n integers starting with 1. And so here we have a little program here written in this Apollo guidance computer assembler. And so we went ahead and used ChatGPT, why not, to write the same program. And voila, here's what ChatGPT came up with to do this. And again, this probably works. The only way to test it is to go ahead and you implement that instruction set. If we tried to do this in Python, for example, sum the first integers starting from 1, then in Python, here's a program here that I believe does that. And if we went to ChatGPT and asked it to write a Python program, then it would write this program here. And here it goes. So here's some examples. We now have to take the programs that we're talking here, and we have to compile them. So the compiler is a program that translates the code written in this programming language into another language. So there's a series of well-known steps. There's first of all, a lexical analysis, where the compiler breaks the source code into tokens that represent the individual elements of the program. Here, for example, there'd be a lot of syntax errors that would be caught. There's a syntactic and semantic analysis, where the compiler checks the syntax and meaning of the code and builds an intermediate representation of the program. And then finally, there's an optimization stage where the compiler can do some basic performance and efficiency improvements just using this intermediate representation. And then finally, we generate output code that's the final code in the target language that we're trying to get this mapped into. Now, the lexical analysis here is broken down into a set of stages. There's input processing, where you clean up the input text and prepare it, remove comments, white space, other non-essential characters that are, really useful for the human, but they're not needed here. Tokenization is the process of breaking the input text into a sequence of tokens by matching characters in the input text against a set of patterns or regular expressions that define the different types of tokens. There's a token classification stage where we determine the type of each token, so that this might classify keywords, identifiers, operators, punctuation, symbols, each as separate token types. There's the validation of the token. Each token is valid according to the rules of the programming language. So for example, a variable name is a valid identifier, or an operator has the correct syntax, and so forth. Then finally, in the output generation stage, we have the output of the lexical analysis process is typically a list of tokens, and they're passed to the next stage of compilation or interpretation. In the stage for syntactic analysis and semantic analysis, let's go through this one at a time. The functions of the syntactic analysis, also known as parsing, is the process of analyzing the input code to determine its structure and ensure that it conforms to the rules of the language's grammar. The output of this phase is an abstract syntax tree, AST, which represents the structure of the input code in a tree-like format. The semantic analysis does type checking. It ensures that data types used in a consistent way. The definition, label checking, the program should contain all label references, and then a flow control check, which keeps a check the control structure used in a proper manner. For example, there's no break statement outside a loop, as one example. Then we go to the optimization stage. Generally, we implement this using a sequence of optimizing transformations. These are algorithms that take the program and transform it to a semantically equivalent program, but that uses fewer resources or executes faster, or both. So you'll hear different buzzwords here, like peephole optimizations, where you're looking at the one instruction ahead, one instruction behind. And so these are very local optimizations. And then there's much more complicated global optimizations, where you're looking across many, many instructions. The code generation here is really the input to the code generator, which consists of this parse tree, or this abstract syntax tree, that's converted into a linear sequence of instructions using an intermediate language such as 3 address code. And then this is followed by instruction selection, which instructions to use, instruction scheduling, in which order to put those instructions, register allocation, the allocation of variables to process registers. And that does it. So the number of machine language statements for a Java statement, if we take a look at this, we take a simple example that A equals B plus C minus D corresponds to 4 instructions here. Load B, add C, subtract D, and then store an A. And so this is where one Java statement results in 4 instructions. There's an explosion here. We skipped over one thing here. An interpreter is something, a different variation on this, a computer program that executes the instructions written in a high-level language, but it directly executes these program instructions using one of many high-level languages, and then this enables other programs to run on the computer or server. And each program is coded and then checked for code errors line by line. So the interpreter, in some sense, would run more slowly. It would go through line by line and check things. But at the end of the day, that could result in faster turnaround. That is, a lot of simple errors are caught very quickly. Programming languages that are based on interpreters include Python, Ruby, Perl, MATLAB, and PHP. And in the interpreted language, the source code is not directly translated by the target machine, but the interpreter reads and executes the code. Okay, so we have now compilers and interpreters. These are two different types of software that convert high-level programming languages into machine code that computers can actually execute. The main difference between the two is the compiler translates the entire program into machine code before running it, but the interpreter translates the program line by line as it runs. So programs that are compiled into native machine code tend to be faster than interpreted code. And this is simply because the process of translating code at runtime adds to the overhead, and this can cause the program to be slower overall. So here's a little table summarizing these things, compiler versus interpreter, and you can see that this just mimics what we talked about here before. There's also the notion of a linker. The compilers and assemblers generally produce machine code that's directly executable by the computer hardware, but as an option, they can produce an intermediate form called object code, basically the same machine-specific code, but it's augmented with a symbol table with names and tags to make executable blocks or modules identifiable and relocatable. So the compiled programs will typically use these building block functions kept in the library of such object code modules, and a linker is used to combine the pre-made library functions with the object files of the application to form a single executable file, and then the object files are used to generate an executable file that often is produced at different times, sometimes even by different languages, and is capable of generating the same object format. So it gives you a lot more flexibility to use mix and match things. How many instructions does the computer need to solve a typical computation program? Well, it appears that we need something like 5: load, store, jump, add, and subtract. And using the Apollo guidance computer, we have 1, 2, 3, 4, 5 here with these 5 here. But for improved effectiveness, most computers have additional instructions. So the Apollo guidance computer had 33 when it could have actually used perhaps 5. The IBM System 360 had more than 140 instructions with all kinds of variations. The DEC PDP-11 had 138 instructions. So you can see that 5 is kind of the bottom, but the people that actually end up offering commercial products throw in a lot more things, in part to differentiate what they're doing from the competition. How many instructions does a computer need to be useful? Well, the first Fortran compiler for the IBM 360 was developed by IBM in 1964. This compiler was written in assembly language and used only 47 instruction types, and the people that did this were very smart. So they ended up, though, using only 47 out of the 140 instructions that the IBM 360 had for writing the Fortran compiler. And all these other instructions just simply added the complexity or cost of the IBM 360. Here's a picture of the creator of Python here. And the name comes from Monty Python. So its core philosophy is summarized in the Zen of Python, which includes aphorisms such as beautiful is better than ugly, explicit is better than implicit, simple is better than complex, complex is better than complicated, and readability counts. So rather than building all of its functionality into the core, Python was designed to be highly extensible via modules, and this compact modularity made it particularly popular as a means of adding programmable interfaces to existing applications. So the vision here was a small core language with a large standard library and an easily extensible interpreter, stemming from all of his frustrations he had with another high-level language which espoused the opposite of what we see here. And this has led to a great deal of popularity. Python, for example, has picked up a lot of statistical capabilities and increasingly is used in finance and in genomics types of applications. So in summary, how did programming languages evolve? Well, we picked out Fortran in 1957, developed by IBM. Fortran is a formula translation language, really the first high-level programming language for scientific and engineering calculations. We also had Lisp in 1958 for Lisp processing, which was created for artificial intelligence research. And it introduced the concept of symbolic expression processing, and is still used in AI and in symbolic computing. COBOL in 1959, Common Business Oriented Language, was designed for business, finance, and administrative systems, and is still there today in many applications. ALGOL, which was developed 1958 to 1960, an algorithmic language, influenced many subsequent languages, building block structures, lexical scoping, and syntax formalism. BASIC, which I believe came out of Dartmouth, was a beginner's all-purpose symbolic instruction code, BASIC, for educational purposes and for simplicity. And it went a long way toward popularizing computer programming. And in fact, I believe this is what Gates and his partner developed for this very first personal computer in 1975 was a BASIC interpreter. C was developed at Bell Labs by Dennis Ritchie and became widely used due to its efficiency and portability, and it served as the foundation of the development of the Unica operating system. So it includes sophisticated data structures like pointers, but it also has an engineering balance, so you can actually mask on the register, and this is very useful for doing device drivers. So rather than being religious about this, C attempted to encompass both being useful but pushing the envelope on what's going on. We also had Pascal, which was designed for teaching programming. It had nowhere near the same popularity as C, but it's still there in this journey. C evolved into C++ in 1983 with much more object-oriented programming features. But again, if you don't use these, you can just stick with C and knock on wood, do fine. The object-oriented programming paradigm was very different than procedural programming, and this led to the ability to break things up into modules, and each module could be debugged or tested one at a time. And then when they started to piece them together, you could see what interactions led to what failures. And so it was very easy to build very large, complicated applications or programs using this technique, where it was very difficult with procedural techniques, because every time that you added something, you had to do regression testing on everything. Whereas in the object-oriented programming, if something broke and I just added one module, then I would go to that one module because everything else worked. I knew it worked before that. Java in 1995 was developed by Sun Microsystems, very popular for web development. Python came out in 91 and is known for readability and simplicity, widely used first language in many colleges. JavaScript, Ruby. Ruby is really gaining popularity as a framework for developing programs here. C# was pushed by Microsoft. Rust, which appears to be coming on, has a real focus on memory safety, memory leakage, where people allocate memory and then forget about it, rather than when they finish using it, they should return it to memory. That's a standard error that occurs in many applications. And so this is gaining in system programming popularity. Swift, which is developed by Apple, is used for the Mac OS, iOS, all of the iPhones and Mac computers and the Mac applications and so forth. And it's felt to be more modern and safer compared to Objective-C, which we didn't even list here. And then we had this tensor language, which is this programming language for very high performance computing involving sophisticated data structures. So here's some references. These all have hypertext links to them that you can go through and see what's going on. And with that, we're done. I'm going to give you a short bio on who I am. I spent 8 years at MIT as a student. I went to Bell Laboratories and spent 12 years there, where I lectured at over 50 universities and research institutes in North America, Western Europe, Soviet Union, and Japan. I worked in depth on 20 different Unix application systems and consulted on another 80, creating a class for a master's level computer science program at Bell Laboratories. This class was taught at Columbia University 3 times, and it led to a book that you can buy on Amazon, shown here, a computer and communication network performance analysis primer. And I've spent a lot of time doing independent consulting and venture capital activities since then. So with that, I want to thank you very much. And if you have any questions, email me, bartstuck@gmail.com, and we'll wait to hear from you. Have a good day.